The Java programming language originated at Sun Microsystems in 1991 as part of a research project to develop a programming language called Oak that would bridge the communication gap between many consumer devices such as video cassette recorders and televisions. Specifically, a team of highly skilled software developers called the Green Team wanted to create a programming language enabling consumer devices with different central processing units to share the same software enhancements. Now, this initial concept failed after several deals with consumer device companies were unsuccessful. So the Green Team was forced to find another market for their new programming language. Now, fortunately, the World Wide Web was becoming popular, and the Green Team recognized that the Oak language was perfect for developing web multimedia components to enhance web pages. These small applications, called applets, became the initial use of the Oak language, and programmers using the internet adopted what became the Java programming language. Now, the Java programming language was designed to be object-oriented, distributed, simple, multi-threaded, secure, and platform independent. So let's take a look at each of these items. Now, the Java programming language was designed from the beginning to be object-oriented. But what does that mean, object-oriented? Well, the best way to understand it is first to look at how programs in the past have been structured. So let's go ahead and click on the Procedural tab. You see, in a procedural program, a program is broken up into a series of steps. You perform step 1 or task 1, and then the next step, and then the next step, and then the next step, in a very linear fashion. So how does that differ from an object-oriented program? Well, click the Object-Oriented tab. You see, in an object-oriented program, our focus is on objects, these autonomous pieces of code that interact with each other. They have state, they have attributes, they have operations, and they can talk and communicate with one another and adapt to different situations. So for instance, we might have a customer object creating an order object, or a bank object opening a new account object, or something like that. So the focus in a procedural program is on the steps, whereas the focus in an object-oriented program is on the objects that will perform the operations of the program. The Java programming language was also designed to be distributed. Now, unlike programs in the past where all the pieces of the program had to be together at the beginning of the program's execution, a Java program can actually have its pieces scattered all over the place, even all over the internet. And as it executes, it will bring those pieces back together as it needs them. Now, this is done through things like remote method invocation and common object request broker architecture. Now, these topics are very advanced, and we won't be covering them in this course. But it is something that you need to understand is capable with the Java programming language. Another big design consideration for the Java programming language was that it should be simple. Okay. A lot of you are going to get done with this course, and you're going to say Java is not simple. So let's say simpler. It was meant to be simpler than languages such as C++, which had come before it. You see, in a language like C++, you've got lots of places you can get yourself into trouble. You can access memory directly. You have to remember to deallocate the memory that you've allocated. You have this thing called multiple inheritance. There's lots of places that you can run into problems. So they wanted to get rid of those areas and minimize the risks involved with programming with Java. And for the most part, they've done it. So instead of using pointers, you use references. You no longer have to remember to deallocate your memory because there's a garbage collector to do that for you. Multiple inheritance, they got rid of it. You only have single inheritance. So it's things like that that they've been able to simplify, which does make Java a much simpler language than something like C++. The designers of the Java programming language knew it was important for Java to support multi-threading. But what is multi-threading? Well, basically, it's the ability for a Java program to carry on several tasks at the same time. For instance, one thread could be accessing a database, while another thread is printing something out to a printer, and yet another thread is updating the user interface. Now, this topic is beyond the scope of this class, but it is a very important feature of Java, and it's used in things like web servers and database servers. One of the great features of the Java programming language is its built-in security. You see, every Java program is executed in what's called a Java virtual machine. Now this Java Virtual Machine, which we're going to talk about later, interprets the Java code and executes it. But before it executes the code, it makes sure that the code doesn't have anything that's unsafe in it. For instance, it will not allow the program to directly manipulate memory. It also will make sure that all the code is valid, that no one's tried to slip something in there that shouldn't be there. And it also, for instance, will not allow an applet to read or write from your hard drive. The last key design feature of the Java programming language that we want to talk about is its platform independence. And this is probably its most important design feature. But before we can do that, we first have to take a look back at how programming languages in the past have been compiled and executed. You see, in the past, what you had to do is you took your source code, let's take the C language for instance, and you would take and you'd run that source code through a compiler. Now that compiler had to be for a specific platform, such as Solaris, Linux, or Microsoft Windows. That compiler will give you out a binary file. Now that binary file was platform dependent. It could only be executed on that particular platform. But before you could execute that binary, you still had to run it through what was called the linker. And again, that was platform dependent. Now that linker would take a bunch of files together, some other binary files, and bring all those libraries of code together to get you one last file, which was your executable file. Now this executable file could actually be run, but it could only be run on that particular platform. So the Solaris executable could run on the Solaris workstation, the Linux executable on a Linux workstation, and the Windows executable on a Windows workstation. Unlike a language like C, the Java programming language provides us with platform independence. You see, now we're able to write a program once, compile it once, and be able to execute it on a variety of platforms. So let's see how this is done. You see, we take our source code and we run it through the Java compiler. Now this compiler provides us with output which is called the bytecode. Now this bytecode is very special. You see, it's not for a particular platform. It's not for Solaris, it's not for Linux, and it's not for Windows. And what that bytecode does is it gets interpreted by the Java Virtual Machine. Now the Java Virtual Machine is specific to a given platform. But since there's one for Solaris, and one for Linux, and one for Windows, our bytecode can be run on those different platforms and many others. Now it's time for a self-check to see what you've learned. After you've answered each question, click Check Answer to see if you're right, or to see what the correct answer is. Using Java technology, we can build a wide range of applications. But in order to do that, we need to know which Java technology product group to download and install. Now there's three of them. The first is the J. Using Java technology, we can build a wide range of applications. But in order to do that, we need to know which Java technology product group to download and install. Now there's three of them. The first is the J2 SE. That stands for Java 2 Standard Edition. Now using this, you can build desktop solutions, such as standalone applications like your word processor and spreadsheet, or distributed applications and applets. The second product group is the J2EE. That stands for Java 2 Enterprise Edition. Now using that, you can build powerful multi-tier enterprise apps and e-commerce applications. In fact, many of your popular websites are using J2EE technology. And lastly, there's the J2ME. That's the Java 2 Micro Edition. Now this you use when you need programs with a small memory footprint for use in things like cell phones, PDAs, and TV set-top boxes. In this class, we're going to be using the Java 2 Platform Standard Edition JDK. That's the development kit. Remember, the Standard Edition allows us to write standalone applications and applets. Now with the development kit, you get several major components. The first component is the Java Runtime Environment, otherwise known as the JRE. The JRE allows you to run Java programs, and it includes the Java Virtual Machine, otherwise known as the JVM, and the Java class libraries. Now the JRE is also a separate download, so if all you want to do is run applications, you can download the JRE by itself. We also get the Java compiler. This allows us to write and compile Java programs. You can also get the class library documentation, but this comes as a separate download. And lastly, the JDK comes with some utilities and some program examples to help us learn Java programming. There are 7 stages in the product lifecycle: analysis, design, development, testing, implementation, maintenance, and end of life. In this course, we're going to be heavily involved in the development stage since we're learning Java programming. However, it's very important that we understand all of the stages and what is done in each of them. In the analysis phase, the development group is responsible for identifying an already existing problem which needs to be solved, or for defining a new idea for an application. Once that problem or idea has been identified, they need to determine the scope of the problem, or its boundary. Once that boundary has been determined, they can then identify the key major components that fall within that boundary and fall within the scope of the project. In the design phase, the development group will determine how the major components will fit together to solve the problem or to create the idea. Once they determine that, they can go ahead and individually design each component and create its specifications or blueprints. In the development stage, the development group will take the component blueprints and create each individual component. Now for us, since we're working with Java, this is where we'd start doing our Java programming. In the testing phase, we are now introduced to a new group, the test group. It is their job to take each of our components and run them through a variety of tests to see if our component makes it or breaks it. Once we finish with the development and testing stages, it's on to the implementation stage. In this stage, we're going to get our product out to our end users or our customers. Now, once it's been out there a while, we may find that not everything works the way we thought they would. In that case, we have to go into the maintenance stage and fix those things or tweak those things that need fixing. Now, once we've done that for a while, we're going to get tired of that old product and we're going to want to get on to the better and newer product. And that leads us into the end of life, when we replace the old product or old version with the new improved product and the new version. Now it's time for a self-check to see what you've learned. After you've answered each question, click Check Answer to see if you're right, or to see what the correct answer is. In this module, we describe the key concepts of the Java programming language, such as it's object-oriented, it has multi-threading capabilities, and it has security built in. We also identified the 3 Java technology product groups, the J2SE, the J2EE, and the J2ME. Lastly, we summarized each of the 7 stages in the product lifecycle, including the analysis and design stages. In this module, we're going to use object-oriented analysis and design to analyze a problem and design a solution. In the previous module, we discussed the 7 stages of the product lifecycle. In this module, we're going to take a more in-depth look at the analysis and design stages, but we're going to do it from an object-oriented perspective, because remember, Java is an object-oriented language. In this module, we're going to analyze a problem and then design a solution. Now, one of the first steps in analysis is to understand your domain. And your domain would be probably the business you're trying to solve a problem for, or the area that you're trying to create a new product for. So you have to understand that if you're going to be able to create a solution. So we're going to walk through sort of a case study. And we're going to take as our case study a company called Direct Clothing. Now, Direct Clothing sells shirts from their catalog. So we want to understand everything we can about those shirts. For instance, each shirt has an item identifier, or an ID. And that would be just, for instance, its barcode. Then each shirt also comes in one or more colors: blue, red, green, etc. Also, they come in one or more sizes: small, medium, large. They also have a description of each shirt in their catalog that explains the type of material, the style, etc. for that particular shirt. Then each shirt has a price. You have to make money. And then also, Direct Clothing itself accepts checks and credit cards. During the analysis stage, you're also going to have to learn about the current system, if there is one. With our Direct Clothing company, there are currently two ways that a customer can place an order. The first is by calling a customer service representative and placing the order over the telephone. The second is by mailing or faxing in an order form that they get out of the catalog. Now, Direct Clothing would like to offer internet-based ordering, so this is what we will define as our proposed system. So click the Proposed System tab. Now, what Direct Clothing would like the proposed website to do is when a customer places an order, that the item's availability is first checked. And if the item is available, then the order is sent to the warehouse and shipped. But if the item is not currently available, then that order is placed on hold until the item is available. And then once that item comes in, then the order gets sent to the warehouse and shipped out. Another very important task during the analysis stage is to make sure that we've correctly identified our problem domain. That is, the scope of the problem that we are going to solve. You see, a lot of times projects add things that shouldn't be in there, or they forget things that should be. So we want to make sure that nothing gets left off or nothing extra gets added on. For instance, with our Direct Clothing example, we are building an order entry system. So we want to be able to take orders over the web and then hand those orders off to the warehouse and shipping department. Our system should not be trying to keep track of trucks and their schedules, for instance. That would be outside of the scope of the problem we are trying to solve. So at this point, we've learned a little bit about the problem that we're going to solve, the current system that exists, and the new system that we're going to build. But we are doing object-oriented analysis and design. So we're going to have to start talking about objects and the objects that we're going to build for our system. So what is an object? Well, an object can be something physical or something conceptual, and we're going to represent that physical or conceptual object inside the computer. For instance, a shirt is a physical item, and we might represent that as a shirt object inside of our program. A bank account is a conceptual item, and again, we might represent that inside our program. Now, objects have two main things. They have attributes and they have operations. So let's go ahead and click the Attributes tab and find out what an attribute is. Well, an attribute is basically a characteristic or a property of that object. For instance, shirts have sizes, colors, styles, they have how many of them are currently in stock, and they have their price. Objects also have operations. So go ahead and click the Operations tab. Now, operations are the things that the object. Now that we know what an object is, we must move on to the much more difficult task of identifying which objects we will include in our system. Now, this is much harder than it sounds because we have to do two things. Now that we know what an object is, so at this point, we've learned a little bit about. Now that we know what an object is, we must move on to the much more. So at this point, we've learned a little bit about the problem that we're going to solve, the current system that exists, and the new system that we're going to build. But we are doing object-oriented analysis and design. So we're going to have to start talking about objects and the objects that we're going to build for our system. So what is an object? Well, an object can be something physical or something conceptual, and we're going to represent that physical or conceptual object inside the computer. For instance, a shirt is a physical item, and we might represent that as a shirt object inside of our program. A bank account is a conceptual item, and again, we might represent that inside our program. Now, objects have two main things. They have attributes and they have operations. So let's go ahead and click the Attributes tab and find out what an attribute is. Well, an attribute is basically a characteristic or a property of that object. For instance, shirts have sizes, colors, styles, they have how many of them are currently in stock, and they have their price. Objects also have operations. So go ahead and click the Operations tab. Now, operations are the things that the object can do, the actions that the object can perform. For instance, if we had a customer object, customer objects can place orders and they can cancel orders. Now that we know what an object is, we must move on to the much more difficult task of identifying which objects we will include in our system. Now, this is much harder than it sounds because we have to do two things. We first have to identify some objects, we'll call them the candidate objects, and then we have to determine whether they are appropriate for our solution or not. So the first thing, identifying objects, you must look for those things which have some sort of independent existence. And one way is look for nouns, like order and customer. Now, physical things, like a shirt, are much easier to pick out than conceptual things. And that's why identifying objects is really kind of like an art, not a science. Now, once you have these candidate objects that you've picked out, that you think are appropriate, you must start to ask yourself, are these objects relevant to my problem domain? Are they in my scope or out of scope? So here are some questions you can ask yourself. Does the object exist within the boundaries of the problem domain? For instance, in our direct clothing example, a shirt object seems to, whereas a truck object doesn't seem to fit. Is the object required for the solution to be complete? Again, a shirt object seems to be necessary. Otherwise, how can we have a catalog of shirts to sell? Also, is the object required as part of an interaction between a user and the system? For instance, an order object seems to be how we're going to take the information from the customer and use it inside the system. So an order object seems to be pretty clear that would be included as well. So as you go through these candidate objects, you ask yourself these questions, and you see which ones fit and which ones don't. Going through the steps that I outlined for identifying objects, we've come up with some possible objects for use in our direct clothing example. For instance, we need a shirt object, because that's going to keep track of things like the price of the shirt, the color of the shirt, the quantity they are in stock. We also discussed how we need an order object to collect the ordering information from the customer. We also need a customer object to keep track of the customer information, their name, their address, things like that. Some less obvious ones might be that we also need a catalog. The catalog object is going to keep track of all of the shirts that we have for sale. And then lastly, we probably also need some type of object that will keep track of the form of payment that the customer uses on an order. So these are our possible objects that we might use in the direct clothing example. Now again, we say possible because as you refine your design, you may find that you need more objects, or also that some of these objects you may not need at all. You may be thinking that now that we've identified the objects that we're going to use in our system, that we're finished. Oh no, we're not there yet. You see, we still have to do a couple of things. One, we need to identify the attributes of our objects. Remember from our discussion earlier that attributes are the properties or the characteristics of an object. We also have to identify the operations of each object. And those are the things that the object can do, the functions that they can perform. So let's take a look at the shirt and the order object. And let's see if we can identify those attributes and those operations that are appropriate for each. So the shirt object should be fairly simple since earlier before we talked about all the things that the catalog kept for each shirt, such as each shirt had a shirt ID, it had a price, it had a color, it had a description, and we also have to keep track of how many of that style of shirt we have in stock. So those are going to be the properties that we want each shirt object to maintain for us. For the order, we will need to keep track of an order ID, a date, the total price for the order, and the status of the order. And also, we will need to keep track of which shirt or shirts are on that order. Now that we've identified the attributes for those two objects, we also must identify the operations for an object. So what are those things that a shirt object can do, and what are those things that an order object can do? For instance, for a shirt object, we'll want to be able to add some stock to that shirt. So if we get some more shirts in, let's say we get the blue color shirts in, large size, we're going to want to add those to the stock. Let's say we get 15 of them in. Okay, so we need an add stock function for shirts. Let's say we decide that a shirt isn't selling and we want to ship it back to the manufacturer, so we'll need a remove stock function. Or also, every time someone orders a shirt, we'll need to remove that stock from that quantity of the shirt. We also will want to be able to display the shirt information. So we'll need a function that does that. That'll do that on our catalog, on our website. So those are just some of the operations that we may identify for shirt objects. We also need to identify some operations for the order object. For instance, we're going to have to be able to add shirts to the order. So the user's filling out the order form and they're going to be buying shirts. Every time they say they want a shirt to add to the order, we'll call this operation and have the shirt added. Let's say the user decides they don't want a particular shirt. We'll need to be able to remove that shirt from that order. So that's another operation we'll have to define. Once the user's done filling out the order and adding shirts to it, they'll need to be able to submit the order for processing. And also, if we find out that there aren't enough quantity of a shirt that they want in stock, we'll need to be able to put that order on hold. So those are the operations for our two objects. Now you need to identify the attributes and the operations for each of the objects. Now at this point, you may be asking yourself, is there any significance to the diagrams that you're viewing? And yes, there is. They are kind of a UML light. UML stands for Unified Modeling Language. And it's just a graphical way of showing what attributes and operations a class has or an object has. So you put the class name or the object name in the top box, you put the attributes in the center box, and in the bottom box you put the operations. And so it's a standard that we'll be using throughout this course. Okay, we're not yet done talking about attributes because I haven't revealed the whole story to you just yet. You see, there's kind of like two different types of attributes. There's those attributes that are specific to that object. For instance, for a customer, their customer ID is specific to that object. Their name attribute is specific to that object. Their address is specific to that object. But there's also information that the customer object needs that really comes from another object, such as the order that the customer has placed. We don't keep that order information inside the customer. Instead, we refer to it. We link from the customer object to the order object. So we're going to have an attribute in the customer object called order, which will provide us a way to go find its associated order object. Same thing with the order object. It will have some information that's specific to it. Its date, its total price, its status. But then it's also going to need information about the shirt objects which have been purchased on that order. Now we don't keep that information inside the order object. Instead, we'll create a link to the associated shirt objects. And so we'll do that with an attribute. And we'll see how this is done as we move on through this course. But this way, we don't have any duplication of data. Each object keeps its own data, and if it needs to access data from another object, we create a reference to that other object or a link to that other object. Earlier, we identified the objects that we're going to have in our direct clothing solution. Now we've gone back to those objects and we've added the attributes and the operations as well as the links between the objects for each of these. So let's go ahead and take a look at some of these. For instance, the catalog object has a shirts attribute. This shirts attribute is a link or a reference to all of the shirts that are in our catalog. We also have a add a shirt and a remove a shirt operation. The order object has attributes order ID, total price, status. It also has links to all of the shirts that are on that order, as well as a link to the form of payment that the customer used to pay for the order. It also has add shirt to order operation, remove shirt from order, submit order, and put order on hold, which we discussed earlier. Now, why don't you go ahead, take a look at the other objects that we've identified, and see if the attributes and the operations and the links make sense to you. Okay, we've now identified the objects that we're going to have in our system, but we're not done yet. We now have to design our classes. Well, what's a class? Well, A class is a blueprint for creating our objects. So let's go ahead and take an example. Let's say home building. Let's say we have a home builder that wants to build a certain style of house. They're going to go ahead, and the first thing they're going to do is they're going to make a blueprint. Now that blueprint isn't the house, it's just the plans to be able to build a house in that configuration and that style. So for instance, like Monterey. So using the Monterey blueprint, our builder can build as many houses in that style as they want. Now if they want other houses in different styles, they'll have different blueprints for each of those house styles. So for instance, Santa Fe and Hacienda. That's the same thing that we do with our objects. To be able to create objects, we have to first start with a blueprint. So to create shirt objects, we need a shirt blueprint. To create order objects, we need an order blueprint. And to create customer objects, we need a customer blueprint. Now those blueprints are called classes. So now we're moving from analysis into design. So we're going to design our classes. Before an analysis, we were identifying objects. But now we need to design the classes, because the classes are the blueprints that are going to create our objects. So we've done most of the work now. Now all we have to do is just sort of convert that object definition to a class definition. And so the way we do that is we just get it closer to the Java language. So we use our same symbols that we did before. So that's the 3 boxes. And now we're going to use a squared off rectangle instead of the rounded rectangle to indicate that this is a class, not an object. So again, in the first box, we're going to put the name of our class. Remember, before it was the name of an object. Now it's the name of a class, so it's going to be shirt. In the middle box, we're going to put our attributes. But now instead of saying like shirt space ID, we're going to have to get closer to the Java programming language, because this is going to be the design document where we're going to work from this point forward. So we say shirt ID, and we follow the Java naming conventions. Now we haven't talked about those yet, so you'll learn that as you go along. But basically it'd be shirt lowercase s followed by ID capitalized. Price lowercase, description lowercase, size lowercase, color code with a lowercase c in the beginning and a capitalized C in the middle. And we'll talk about those naming conventions later. Same thing with the methods. What were operations in our analysis phase now become what we call methods. Methods in Java are the operations of the object. So, for instance, calculate shirt ID, display shirt information. Notice we don't have spaces in there. Before we had spaces. We had display, space, shirt, space information. Now it's all one word, because that's how method names have to be. Again, we haven't talked about that yet, but we'll be getting to all of that in the next module. In this module, we walked you through a very simplified example to try to illustrate what takes place during the analysis and design phases in an object-oriented project. Now we've greatly simplified the process, and there's a lot more that takes place in those 2 stages, but that would be an entire class all on its own. And this class is really focused on Java programming, so we're really focused on the development stage. But we wanted you to get a taste of what happens in the stages before we get to the development stage.